Hey guys, Mr. Bowman here. Today's learning objective is in green. We're learning to determine the equation of given graphs, and emphasis added, we're going to do that through considering their features. On the right hand side of our screen, I've got 5 graphs. They have limited domains, but they are a mixture of what we've learnt throughout this topic. And what we're going to do, graph by graph, we're going to go through its features. We're then going to go through determining its equation as well. We're going to start off with equation 1, so we'll do that here. Equation 1. The first step we'll need to do, just like we'll need to do for our tested internal, we need to run through the features of that graph. So for me, the obvious feature is, well, it's a straight line. It has x and y intercepts that we can see. So it has a y intercept at 0, 6. It also has an x-intercept at 6, 0 down there. The other thing is the gradient. We can identify the gradient using rise over run, and we can see for every one it goes down, it goes across 1. Down. So that idea of the gradient, it's pretty symmetrical. It goes down at the same rate. So the gradient will be equal to 1. And the other thing I'd like to note is that has a domain that's been limited. And that domain sits between 0 and 6 for the x value. So if you're looking at this thing here, so in theory it should go over, but we've stopped it at 6. And it should carry on that way, but we've stopped it at 6 as well. Using all of that information, we can actually come up with the equation. So the equation of a straight line, y equals mx plus c, m being the gradient, c being the y-intercept. So in this case, our equation would have been, that gradient is -1 because it's actually going downhill. So gradient of -1. So our equation would have been -1x plus c. You also might have written it as 6 minus x. And don't forget about the domain over there. So let's write that on our formula list. So equation 1, y is equal to 6 minus x with a domain that sits between 0 and 6. So that's equation 1 done. I'm now going to pause the video. I'm going to clear our working to date, and then we're going to shift on to question 2. Okay, that's all cleared. We are now going to change pen colors. Let's go for blue, and we're going to have a look at equation 2. So the first step is we do need to run through all of the features that could help us determining what equation or feature it could be. So for me, the obvious one is it does look like a wave, which suggests it could be a trig function. And specifically, it could be sine or cosine. Probably not going to be tangent given the way it looks. The next one, it does have a y-intercept. That information is not particularly useful, but that's somewhere between -1.5 and 2. So not sure on the exact value. It does have an x-intercept. It's actually got 2 of them, times 2. And it looks like it's approximately 1 and between 4 and 4.5. So again, not exactly sure on the x-intercepts. I think there's a visible domain here as well. So the domain, it looks like it sits between 0 and 6.5. So I've used that end as an estimate. Hopefully it's around 6.5. Well, I remember that the amplitude is really important for trig graphs. And if you have a look at the middle of our graph, so it looks like that axis is the middle, so the x-axis is the middle, and it does look like it has an amplitude of 2. Amplitude of 2 units. So that tells us a bit about the formula. And I can also see it's got a full revolution in about 2 pi. So full revolution within 2 pi. And that's because we can see it starts here, it goes up, goes down, and it kind of stops or gets back to the original point at just over 6, which is about 6.28, which is about 2 pi. So to me, that looks like one full revolution within that. So it doesn't look like it's been moved up or down because of the x-intercept. So no movement up or down, but it does look like it's been moved left or right because a sine graph, well, that goes in at 0, and a cosine graph, that should come in at 1. So it does look like there's been a bit of movement left or right. So if it started at 0, it looks like it's been moved across 1 unit. Move left by, move right by 1 unit. And if we put all that information together, so our formula y is equal to 2 being the amplitude, so that would have been our a value. And we've decided it's a sine graph because it looked like it went through 0 and it's been moved across 1. In terms of b is 1, so we think there's 1 for revolution, so that's unchanged. X minus 1 because of that movement to positive 1. And it doesn't look like there's any movement up or down, so that d value would be 0. So it looks like we've got the equation of this trig graph. And don't forget our domain, we do need to put that in as well. And it looked like that was capped at 6.5. So let's write that in on a list. So 2 sine x minus 1 with a domain between 6 and 6.5 with respect to the x values. So what I'm going to do is I'm going to pause the video, I'm going to clear all this, and we're going to get into our next example. Make sure you pause the video to get the notes and the features that we're seeing down. Okay, that is all cleared. We're now going to have a look at equation 3, and we're quickly going to run through its features and then come up with the equation. So the first thing is, I think it's pretty obvious, it looks like a parabola. So that's the first really obvious one from there. The next one is, well, it's a positive parabola because it's pointing, or it's U-shaped as opposed to N-shaped. The big one, it has a vertex at -2, 1. We can't see any x or y intercepts. I'm sure they are there, but it looks like the range or the domain has been limited. I can see, like all parabolas or most parabolas, it is symmetrical, and our line of symmetry is at x equals -2. And when looking at the graph, because of the funny numbers for the domains, it's probably been limited by the range. So it's probably been stopped at 6. So it has a range where y is equal to or less than 6. Using all that information, we should be able to figure out the equation of our parabola. So we can see it's been moved up 1. So if we consider our formula, y is equal to ax plus b squared plus c. And I'm using this information because I've got clear eyes on the vertex. So it's been moved up 1, which means that c is going to be +1. And it's been moved across 2, which means the b is going to be +2. From there, we've also got another point, so we can actually mathematically solve to figure out what the a value is. So let's do that slightly over to the right. So at -1, 2.5, we know x is equal to 1 and y, or -1 and y is equal to 2.5. So we're going to put that into our equation. 2.5 is equal to a of x plus 2 squared plus 1. And we also need to add in the x value now. So that's -1 plus 2 squared plus 1. -1 plus 2 is 1. 1 squared is 1. So that's going to be 2.5 is equal to a plus 1, which means a is going to be equal to 1.5. And you also may have put that in a fraction version as well. So what that means is, therefore, our equation y is equal to 2/3 of x plus 2 squared plus 1, and that had a range where y was less than or equal to 6. So let's put that into our formula up the top. So y is equal to 3/2 x plus 2 squared plus 1, with a range where y was equal to or less than 6. So please get that down. I'm going to pause the video and we're going to go through 4 as well. Okay, we're back and we are now looking at equation 4. So the first thing that I can see is it's probably going to be one of those hyperbolas, logs, or exponential graphs. The first thing that I can see is I can see a clear asymptote at 3 just on there. So that's a horizontal asymptote at y equals 3. And that does tell us about some upward movement. So it's been moved up 3. Once we've done that, we can tell there's been, because of the asymptote is there, if we go above 1, that tells us the reference point as to whether or not it's been moved left or right, and it doesn't appear to be moved, so no left or right movements. In terms of vertical asymptotes, I can see that this line continues to move across and it doesn't appear to never reach a point. So that doesn't look to be an asymptote. So there's no vertical asymptote. Sometimes that is difficult to figure out as well. Hopefully you guys can hear me over the rain that has just started in the background. And finally, based on that, it does look like there is exponential growth. And that tells us it probably is going to be an exponential model. So I'm writing down the exponential model equation. As we said, there's been no left or right movement. That means b is going to be equal to 0. It has been moved up 3. So that means c is likely to be 3. So we're going to go y is equal to a to the power of x plus 3. We're now going to use our point that's been given to us. So at point 2, 7, x is equal to 2 and y is equal to 7. So we're going to plug that in. 7 is going to be equal to a to the power of 2 plus 3. 4 is going to be equal to a squared. A will equal 2. And as a result, that means our equation is y is equal to 2 to the power of x plus 3. Apologies about the pen not working properly up in that space. And of course, that had a range of any value above 3. Okay, cleared you question 4 working. We're now on to question 5. So question 5 is our last graph. So the first thing is there's no obvious x or y intercept. There does appear to be 2 asymptotes. So it looks like we've got a horizontal asymptote going along y equals 2, and it does look like we've got a vertical asymptote at x equals 3. And what that does mean, 2 asymptotes, that normally suggests a hyperbola or hyperbola graph. The asymptotes also tell us about the movement up and down. So the horizontal one tells us that it's been moved up 2, and the vertical asymptote at y equals 3 means it's been moved to the right by 3. So I've now got our general formula. If we put our b and c values, so c is how much it's been moved up or down, and we've said it's been moved up 2, and b was how much it moved left or right, and we said that was -3. We can then solve for a. So what I'm going to do is I'm going to pause the video and do the maths just to see what that comes out to. When we follow that through, we plug in our point, we use our algebra, and we figured out that a is equal to 2. So that means y is going to be equal to 2 divided by x minus 3 plus 2. And it does appear that that has a domain that is above 3. Hopefully you found the video useful. Let's get into